Hi, Mick McQuaid here for iste782 Visual Analytics. Today I'd like to discuss Bertin's theory of data visualization, which we touched on last time. We're going to go into a little bit more depth today. Jacques Bertin's landmark book, Semiology of Graphics, presents a theory of what we now call data visualization, but which Bertin referred to as graphics. His theory is a sign system of graphics. Semiology is the study of sign systems. And here are some sign systems and their meanings. So monosemic, I actually don't know how you would pronounce that, but I'm just going to say monosemic system can be math that can be expressed by sound, so we can actually, recite equations, or by sight as graphics. A polysemic one that we can express by sound is language. By sight, we can represent figurative imagery. And a pansemic system would be by sound music, or by sight abstract imagery. So, and let me just go back to that for a second, because let me just draw a distinction between graphics, figurative imagery, and abstract imagery. So graphics that we're talking about here could be something like a bar chart. Figurative imagery could be something like a portrait of a person. Abstract imagery could be something like Kandinsky's famous picture of circles. Graphics are a visual spatial system. Graphics have at their disposal the variation of marks and the two dimensions of a plane as visual variables. And Bertin calls these retinal variables. The visual variables are retinal variables. And the relationships between these visual variables can be perceived instantaneously. In contrast, a linear system such as speech requires an instant for each sound. The information that is to be transmitted is content. The graphic system is its container. Bertin uses the expression translatable content of a thought to characterize information. Bertin is not at all concerned with persuasion, so let me just as a sidebar say that we're not going to be talking about persuasion today. There is a contemporary researcher named B.J. Fogg at Stanford with a lot of followers who focus on persuasive graphics. That's a different thing. Bertin is only concerned with the limits of the sign system. Does a given graphic convey what it means to convey? That is the question to be answered with Bertin's theory. Whether the graphics are truthful or misleading, that's a separate question. That's outside the definition of the sign system. And personally, it's my opinion that you need to understand these. You can think of the sign system as the building blocks with which you can put together a structure that could be an argument about truth or misleading in graphics. In other words, to speak at a more sophisticated level, to speak at a subtler level, you first need to know the basics. I don't believe that it's fruitful to talk about the notion of persuasive graphics without understanding some of the principles of graphics first. So let me just expand on that for a moment. So I think that a course like this is a prerequisite, or should be a prerequisite, to talking about persuasive graphics. You should learn this stuff first, and then you can say something that's sophisticated and insightful about persuasive graphics. I think it's a mistake to just begin with the study of persuasive graphics. The invariant is whatever is common to all correspondences in information. The variational concepts in information are the components. These two terms, invariant and component, are key to understanding the theory. You can think of the invariant as the title of a given data visualization, the thing that summarizes the entirety of it. The components, on the other hand, are the things that vary in a given visualization. In a stock price chart, the stock is the invariant and the price and time are components. The very first step in analysis is to determine the number of components. That is because the eye can only distinguish a small number of variables. So the component The components are the content of the information that varies, such as the price or date. The variables are the visible marks used to represent the components. Here's an example. Here's an high-low, open-close stock price chart for 4 days. The tick mark on the left of each vertical line tells the open price for that day. The vertical line itself tells the variability in price during the day, and the tick mark on the right is the closing price for that day. So those are visual variables that represent the stock price. The stock price is the component. So the price itself is the component, and the date is another component here because this is over 4 days, so each one of these vertical lines represents a component. But they represent the component through a visual variable, or a retinal variable, as Bertin would call it. So you have to sort of get this distinction between the concepts and what we use to represent the concepts. Length is a property of both components and variables. It is the number of categories of the component or variable. So for example, state is a component in a picture of the USA, and it has length 50 because there are 50 states. On primitive computer displays, early computer displays could only display one color, but after that there were some that could display only 16 colors. And so there is a palette of 16 common colors that were displayed by those early computers that's still in use today. So there the color is a retinal variable and has a length of 16. Okay, and then levels of organization. So every component is located on one of 3 overlapping levels. First is the quantitative or interval ratio level using countable units. Second is the ordered level involving all concepts permitting a ranking. And third is the qualitative or nominal level that includes all unordered groupings. Bertin avoids time, so he eliminates animation from the scope of the graphic system. So the graphic system's realm is only what can be perceived in an instant. So there's a lot of stuff to analyze after Bertin. Bertin, by the way, was a cartographer who lived to be, I think, 104 years old. So he lived in 3 centuries. He was born in the late 1800s and died in the early 2000s. And most of his work was as a cartographer as a young person, and his graphic system really reflects that. Really reflects coming from the perspective of reading maps, and particularly reading specialized information-intensive maps. So there are 8 variables within the scope of Bertin's graphic system: the 2 dimensions of the plane, x and y, size, value, texture, color, orientation, and shape. Each mark that is signified by the 8 variables can represent a point, or a line, or an area. And each graphic is one of 3 kinds. It can be a diagram, it can be a network, or it can be a map. So a diagram depicts the correspondences between 2 or more components. So an example would be a picture of stock price over time. A network can depict correspondences within a component, as in a network of conversations between individuals. Or a map depicting, spelled wrong here, correspondences among elements of a geographic component, such as a map of dairy production among states of the USA. The 6 retinal variables are the 8 variables minus the x and y coordinates. So size, value, texture, color, orientation, and shape is what Bertin uses to refer to as the 6 retinal variables. So the basic graphic problem is that you have so many choices with so many variables and so many ways to use each of those variables. You have many, many choices. So a basis for choice between many possible graphics is this: if in order to obtain a correct and complete answer to a given question, all other things being equal, one construction requires a shorter period of perception than another construction, we can say that it is more efficient for this question. So this introduces the notion of efficiency in graphics. So the one that you can glance at and get the answer really quickly, that is the efficient graphic. There are 5 aspects of Bertin's image theory. First is the stages in the reading process. Then are the possible questions, the levels of reading. Then is the definition of an image. Then the construction of an image. And finally, the limits of an image. So the stages in the reading process are as follows. External identification, what components are involved. Internal identification, by what variables are these components expressed. So remember, the components represent the concepts such as the price. The variables that expressed those in the chart that we looked at before were lines. The perception of pertinent correspondences. What are the pertinent correspondences between components? For example, what is the given stock price at a particular moment? We can tell that from looking at the chart. Second, possible questions, levels of reading. So there are questions introduced by one element of a component, resulting in a single correspondence, which is the elementary level. There are questions introduced by a group of elements in a component, the intermediate level, reducing the length of the components. And finally, questions introduced by the entire component, the overall or global level, reducing all information to a single ordered relationship. There are as many types of questions as there are components, and for each type there are 3 levels of reading, and each question can be identified by its type and level. Third is the definition of an image. The meaningful visual form perceptible in the minimum instant of vision is an image. The most efficient constructions are those in which any question can be answered in a single image. The image is not the same thing as the figure, which includes everything seen in a frame. A single figure may include many images, not necessarily as separate constructions, but with individual instants of perception. The image is built upon 3 homogeneous and ordered variables, the 2 dimensions of the plane and a retinal variable. All information with 3 components or fewer can be represented as a single image. An image will not accommodate more than 3 meaningful variables. All information with more than 3 components cannot be constructed as an image. It is necessary then to choose preferred questions and construct the graphics so they can be answered in a single instant of perception. The functions of a graphic representation are recording information, communicating information, and processing information. So recording information is creating a storage mechanism to avoid memorization. Communicating information is creating a memorizable image to inscribe the information in the viewer's mind. And processing information, finally, is to permit a simplification and its justification. The rules to define the most efficient construction for a given case are represented by the standard schemas, which are shown on the next slide. So these are the standard schemas. Now this diagram, which shows the possible representations along one side, diagrams, networks, and maps, and the number of components across the top, and finally a comprehensive image, processing graphics, and inventories. This diagram, which comes from page 172 of Bertin's book, uses Bertin's notation to depict what he calls the standard schemas. These are the schemas that represent the ideal combinations of visual variables to depict different kinds of information. Notice that elements are additive in the horizontal direction for each kind of imposition. You need to consult the tables on pages 56 and 57 of Bertin's book to fully appreciate them. For example, the letter O means ordered and suggests that in most cases visual variables capable of ordering are required. The orthogonal arrows mean that the planar dimensions are required, while the circular arrow signifies that a network arrangement, for example, the spokes of a wheel, is required. The diagonal arrow means that elevation above the plane is required, and that refers to the 6 retinal variables. And the variable n signifies that at least n images are required in a figuration. And that's all that I'm saying on this slide here. Okay, now the rules of construction govern the choice of visual variables, but they can still be used well or poorly. So we need rules of legibility arising from the need to accomplish sensory differentiation. And these fall into three categories: graphic density, angular separation, and retinal separation. Bertin distinguishes between what is seen and images. So he contends that there's an optimal number of marks per square centimeter, and he claims that 10 is the maximum number for a figuration. Yet there is no upper bound for an image because of its definition as instantly perceptible. Too few marks per square centimeter represents an underutilization of the graphic capacity. And there has been research done on Bertin's contentions. His contentions came from his own observations rather than from empirical studies. Angular legibility results from a compromise between two potentially contradictory rules. So on the elementary level, optimum angular legibility is located near 70 degrees. On the overall level, the image tends toward the form of a square where optimum angular legibility is provided by the diagonal. So here's an example of legibility. So figure 1, the top one, is too flat for the overall trend to be apparent, but it's ideal for elementary readings of individual yields at different points in time. Figure 2, the middle one, is ideal for showing the overall trend, but the angles are too severe to read at the elementary level. And figure 3 finally is a compromise between figures 1 and 2. And that's all that this slide says. Retinal legibility. So the total amount of black should vary between 5 and 10% as in figure 2. Figure 1 has insufficient black and figure 3 has too much. Now, I should comment that although I certainly am not one to disagree with what Bertin says, we have tools available today that Bertin didn't have readily available. So for example, when I make maps like this, I might make the circles quite a bit larger than Bertin would make them, and then make them largely transparent. So I might go close to the size of figure 3 and decrease the opacity of them. And that's just not something that was possible with the technology Bertin was using. So I think that although these rules are extremely valuable, there are places where you will find advances in technology allow you to bend or break them. The subject matter must be separated from the background, as in figure 5, not figure 4. So in figure 4, the subject matter is almost an afterthought. In figure 5, the subject matter dominates. And I think that idea is what Bertin is getting at, rather than this particular method, which was ideal with Bertin's technology, but may not be ideal with our technology. We have the ability to do other things to make the subject matter come more into focus. Quantitative perception depends on the utilization of the maximum range, that is, the ratio of the smallest to largest signs in a series based on size differences. Selective perception is augmented by combinations of retinal variables, starting on this slide and continuing on the next one. So we see we have a point, line, and area, and we can add orientation to any of the three. Then we can add shape to any of the three. We can add value to any of the three, and finally we can add size to any of the three. So we can get a more sophisticated picture with greater retinal legibility based on selective perception. Okay, so we have described the vocabulary for some of Bertin's theory and glanced at the rules for the construction and reading of efficient graphics for answering specified questions. Bertin's book is a lot longer than this slideshow, and there's a lot more to it than this, but this will give us a good start for talking about what we're going to turn to next, which are going to be people who have based their ideas on Bertin's ideas. So there are more contemporary forms of graphics, including some of the most popular forms of data visualization today, that are based squarely on Bertin's theory. So thank you very much for your attention. Until next time.